Alright, hello. So today I'm going to be explaining a theory that me and a few of my friends came up with. So let's go back to the beginning. So I was with my friend on a trip, and my friend so we were just chilling in some building like this. And we were gonna do abseiling, which is basically just rappelling down a building. So looks something like this, but you know, a lot more realistic. So me and my friend were kind of bored, so my friend asked a pretty interesting question to me. Yeah, he asked this. What does nothing look like? And of course, I had no answer because, well, I don't know. But what I did know is how you could use it. So eventually, I thought to myself, and I remembered I watched a video about entropy and how cold spaces always try and equalize temperatures with hot spaces. So I thought, nothing, right? My handwriting is absolutely terrible. But I thought of it like this, right? Nothing has to be 0 Kelvin, 0 bar, and just 0 everything, pretty much. So I thought to myself, if those parameters are 0, then if there really is a nothing that exists, it has to create a force, right? An attraction force. So I thought to myself, what's an attraction force, right? And I thought, gravity. Which, debatable, but yeah. And so when we got back home from the trip, I looked it up and to see if there were any forces that we couldn't explain. And this came up. Dark matter. Can't write on a computer, sorry. Dark matter, right? And, well, dark matter was kind of just scientists saying, we didn't really have an answer to why there was extra gravity, so we just created a constant to fill it in. But if you think about it, right, space isn't empty. In a lot of places, space is full, right? And so, where space is full, you obviously see gravity because there's mass, but where space is full, it's pressurized, and usually pressure leads to heat. So, pressure and heat contrasted with no pressure and no heat, right? And if you think about it from an entropy standpoint, that has to warrant an attraction force. So I looked into, you know, what dark matter was, and scientists didn't really have an explanation. So I drew this model. So this is the curvature of space-time, right? So this is the curvature, right? And you also have, So you've got all three dimensions and then the fourth dimension, time. So if you think about it, right? Say this was a mass here. Say it was a star. This is a mass of 9 billion kilograms. Say, let's say it was 9 billion kilograms. And this is a curvature of, say, 15 billion kilograms. So I had an idea. I wanted to look at an object that's hot and has a lot of pressure. So I thought, the sun. So the sun is made of helium and hydrogen, mostly. There's also some heavy metals, but it's not a huge amount. So the sun, I looked into it, and the sun is 1.4 times 10 to the 27 cubic meters. And then I looked up the weight of 1 cubic meter of hydrogen, helium, just for a high-end estimate. And 1 cubic meter of helium is roughly 0.5. Wait, I forgot what it was, but I think it was around 1/10 of a kilogram. Yeah, it was around 0.15 kilograms. So I thought, if my theory is real, then this will not be the weight. It won't be 0.15 times 1.4 times 10 to the 27 kilograms, because if my theory was true, it would be much heavier because the sun has a lot of heat. So I looked up the weight of the sun, which was measured by gravity and not by volume, and that turned out to be 1.9 times 10 to the 30. So this number is not what you get if you multiply 0.15 by 1.4 times 10 to the 27, because you'd get something smaller than 1.4 times 10 to the 27. So I did the maths, and it's roughly 100 and something times heavier than it should be. I'm not sure exactly, but it's around 100 times heavier than it should be. And that does not line up. So, I mean, yeah, I guess. And for that, I just really didn't think much of it, and I didn't really have anyone to prove or disprove it who actually knew what they were talking about. But yeah, this theory is mostly made from logic and not really maths or anything, so it's gonna need some more proof before it can actually be real. But let me try and draw a diagram here. Say this was, again, the curvature of space-time. So here you have it bent in this dimension, and this dimension. Okay, so these models don't really line up, so let me just make them line up. Okay. So then, you can draw let me straighten this out. Okay, so then you can draw an object like this to represent curvature of space-time. Again, still doesn't really line up, so I think I might just have to ditch this model. But okay, I'll just have to leave out the curvature of space-time just to make it less confusing. Because, like, I'm sure you guys can understand it, but the positioning is a bit off and angles. So let's draw it this way. So these are the 3 dimensions you think of, right? 3D. But then time is a 4th dimension. It's not physical, but it's a chronological dimension. So you can't really draw that, but nothing, or what I call void spaces, would be, well, one problem I've run into is where would they be? Because if you think about it, well, look, I actually drew it correctly. So if you think about it, mass here, right? But space-time curves in both ways because there is no up or down in space. It's all relative, right? So you draw another curve on the top or bottom half, right? And it creates a sphere. And now a sphere, what do you do with the sphere? Well, if there was nothing, where would it be? Would it be here? Would it be here? Would it be here? Would it be here? Would it be here, 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 or here? It could be anywhere. It could even be here, right? It could be anywhere, 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 literally anywhere. So how do you know where it is? Well, the only way you can know that is by measuring its effects. And, well, there's not really a way to measure its effects, sadly. But one thing that's pretty interesting is something I've discovered, right? So think of just a mass, right? Say it was just a block of tungsten, or not tungsten, just I don't know, let's say this was a block of a gas, I guess. Although should probably be a sphere then. So let's make a sphere of gas. Don't know why you'd make that, but it's okay. Let's make a sphere of gas. This is not a sphere because I can't draw. But this is a sphere of gas right here, right? So what happens when you heat it up, right? it expands in all dimensions. Right? It expands, right? In every dimension, it expands. And so, for a long time, and it's kind of proven now that is because molecules move faster when objects are hot or heated up. But if you've been listening this whole time, you might be able to connect the dots and think, well, hey, if there really is a void space, then that would make an object expand exponentially as it gets hotter. And it does. In space, an object will keep expanding if it heats up. And so if there's no force to counteract that, it'll just keep expanding. And when you think about it, the universe keeps expanding. And it's always expanding. So, if you really think about it, what if our universe was... So, according to the Big Bang Theory, our universe was a singularity. Let's depict a singularity as this blob thingy. A singularity is as dense as an object can get, right? And so, what happens if you just broke it? Well, a singularity is extremely hot and extremely dense. You know what happens to extremely hot and extremely dense objects? They expand. And they become bigger exponentially if there's nothing stopping them. And that's interesting because you know what else is a singularity? A black hole. And so this could mean that our universe was long ago, a very long time ago, a black hole. But it collapsed. And that's really something interesting, but that's up to debate for the origins of the universe. But yeah, there's also that. Now, you might be thinking, how can you use this? Like, what use does this have to literally anyone? Well, you know how the world has this kind of problem that we're kind of running out of energy and stuff, right? Yeah. If it's true, we're not running out of energy. At least not anytime soon, because, well, there's energy right there in gravity. I mean, we can create artificial singularities and extract energy from them using things like thermoelectric generators. And if we can actually harness voids, we can make something like this thingy, which harnesses near infinite amounts of energy from singularities. Because a void is zero, so the only limit is infinity for how much energy you can generate. And I won't go on to that because that's kind of complex and I'm not complex. But yeah, there's a lot of different ways you can tweak this theory and change it and add interesting aspects to it. So I'd really appreciate if someone did just that and helped me find interesting things about this theory, helped prove it, helped disprove it. I don't care, I just need someone to elaborate more on what this theory could mean, because if you think about it, near infinite energy generation, that means we could power the world, right? But could we? I mean, that's up for debate. I mean, you'd have to get resources from Earth, and well, you can't just generate energy. So you can't generate energy technically, you can only convert it. And so if you get resources from Earth, you can never extract more power from those resources than you can extract from the Earth. So would it really power the Earth? There's interesting elements like this when you add infinity and zero into play that just don't really make sense. But yeah, that's why I created this video. I mean, maybe some of you are better at logic and reasoning than I am, and like could help with this. But yeah, it's really interesting because yeah, I don't know, it's just interesting. So if any of you can help out, that would be greatly appreciated. So one way you can help out is by liking and subscribing and commenting to boost this video in the YouTube algorithm, because the more you guys like, comment, and subscribe, the more YouTube will push this to other people. So go ahead and do that, because we want to get this video out to as many people as possible, because the more people we get it out to, the higher the chances that one will actually have something interesting to say. So, yeah, I guess I'll see you guys in another video, and yeah, see ya.